One particularly important class of density curves are called normal curves, and normal curves describe normal distributions. Normal distributions show up in many, many different places in statistics because they describe real data very well. For example, scores on SAT exams, or if we were to, let's say, measure heights. Heights of students would be an example of something that might be normally distributed. So every normal curve follows the same kind of overall pattern. Right? They're always symmetric, single-peaked, unimodal, and bell-shaped. The difference, though, is normal curves are defined by their mean and standard deviation. The curve on the left has a longer standard deviation than the curve on the right. And as a result, the curve on the left is sort of squat. It's shorter with fatter tails, whereas the curve on the right is peaked. It's a bit taller. And in fact, there's a good way to eyeball how far one standard deviation is from the mean. You look for where the curvature changes. So the way to imagine that is imagine yourself skiing down a mountain that's shaped like a normal curve. At first, you're descending at an ever steeper angle as you go out from the peak. However, at some point you find that the slope begins to grow flatter rather than steeper. The point at which this change takes place is one standard deviation, one sigma value from the mean, from the center. You calculus students might recognize this as an inflection point. If you were to trace a pencil along a normal curve, you might feel that change in curvature. Notation for normal distributions is pretty straightforward. If we're measuring some variable x, we would say this, and we read that notation as variable x follows a normal distribution with a mean value of 0 and a standard deviation of 1.